Uh, take me to the bank. Take me to the stove. Hey, what the fuck are you looking at? Okay, so I found this amazing. Oh, hold on. I found this awesome website called organicchemistrydata.org. This website is fucking awesome. So it has all of these natural products and how to synthesize them, the total synthesis. Oh wow, capsaicin. Look at capsaicin, guys. Vanillin. What is this? Ammonium carbonate or something? Ammonium bicarbonate? I don't know what that is. Does vanillin smell like vanilla? Whoa, triphenyl. What do you call that? What do you call that? Oh, wow. What is A? Oh, this is A. Dude, I actually think I'm low-key like I'm kind of getting it. Oh, I didn't fill up my water bottle. Wait, did I? Oh, I did. Nice. Okay. So here, this is pretty badass because this is just, okay, we're making acid chloride. And then we form an amide. That's pretty easy. Total synthesis of capsaicin, not even that hard. I don't know what this is about. What does facile mean? Okay, so I think I want to go through the textbook because for me, I mean, I don't need to go through like reading it as in depth as I did in the past. I feel like that's not actually that productive. But low-key, like, what else do we have here? What else is good? Oh my god! Did you guys see that? What the fuck? All right, well, let's look at that. I mean, why not? I actually don't even know what it looks like. All right, methyl ester. Uh, a weird. Let's see. Hold on. 1, 2, 3, 4, 5, 6, 7. Is this a heptagonal ring? I need a 3D structure of it. Oh, well, but still, I want to drag it around. Is this a heptagonal structure? That looks heptagonal to me. One, two, three, 4, 5, 6, 7. That's kind of weird. Okay, and then we have this ester. So we have a... Alright, so I would assume that the total synthesis kind of pieces together some sort of esterification, but let's figure this out. What is this? Is tall? Wait, but p-tall. What is p-tall? Does that mean paratoluene? It probably means paratoluene. Oh wow. We start with this weird sulfonyl bond. Okay, then we start with methyl acetate. Oh, I don't know this chemistry at all. I don't know this reagent. Silicon trimethyl silicon. I don't know what that's. But you know what I really like about this website? Is this. The name of the reaction is here. You know, carbox ester to aldehyde. So we take this ester and we. Let's see, how did we do that? T-bu aluminum hydride. That seems like a reducing agent. So H comes in and then pops that thing off. That's what I would assume happens. Okay. So, you know, I don't know. Like, I don't know what that's about. All right, let's see. Is there any? Let's just go through it one by one. Abscisic acid. I'm just going to go through and see if there's any I recognize. I didn't know you could do total synthesis of this. It's so weird. This one we'll have to go over. I'm supposed to know this for the test on Monday. I feel like I've heard of this. Biotin. Do you have cam 4? I think it's too easy. This one's pretty cool because the Wittig. I never really loved the Wittig mechanism. I don't know why. I love when they have the yields, man. That's so cool. Morphine? Codeine? What does morphine look like? Codeine and morphine are like basically the same. Alright, so they start with... Is this naphthalene? This is like benzyl chloride? Is that what that is? Wait. What is BZCL? Do they tell you? Oh. I wanted to watch the video about this. A work pet? Okay, that seems pretty dope, but not right now. Oh, nice. My AI got smarter. Oh, okay. BZCL means benzoyl, which makes way more sense. Yeah, because you want an acid chloride. Dude, carbonyl chemistry is like the main thing, bro. So, this alcohol attacks this. Now, what is this? NaNO2? This is a base? This looks like a buffer to me. I don't really get how this works. This is one of those things that we did at the end, which was kind of like electrophilic aromatic substitution or nucleophilic aromatic substitution or something like that. Iron chloride. It's just an oxidation. How do we oxidize a primary amine to carboxylic acid? That's kind of weird. All right, now SO2. Dude, see, this is from so long ago that they're using crazy reagents. I get this part. This part I understand. This part less so. And I don't know why you need to... Oh, you know what I think? I think... Because when you do a nitration, I think that it adds NO2. And then you have to do something else to get it to NH2. Okay, let's look at... so we did morphine. Let's look at something more recent. What is ARBO3? All right, I don't understand any of this. Bruh. Cesium fluoride? Okay, I'm not there yet. This molecule is too complicated, I think. I don't know how to do it. Coddling moth compound? Cubane? Dude, cubane is legit the fucking coolest molecule ever. Is cubane a gas or what? Dude, cubane is fucking awesome. Platonic hydrocarbons? Oh my god, dude. I take it back. This is way fucking cooler. Dude, is this in here? Dodecahedron? Dude, this is like solving a Rubik's Cube. What the hell? Tandem deals Alder? This is one of those molecules, like, is there... mechanically trapped in it? The app being the standard notation for encapsulation? The world's smallest helium balloon. That's so cool. In supramolecular chemistry, all right. So there's levels to this stuff, guys. There's levels to this. That's insane. All right, I gotta keep going through this. We gotta go through all of these. All right, so cubine's pretty cool. Okay, what does dopamine look like again? And what is L-dopa? Oh yeah, dopamine. Oh no, it's 3,4-dihydroxyphenylalanine or phenethylamine, and this is just the amino acid form of it. All right, well that's pretty neat. So if you want to synthesize L-dopa, you start with what? Oh, you know what? This looks like a Grignard reagent. Wait, can you use chlorine as the... We only ever used... I don't know what's going on here. Arbuzov reaction. Hydrolysis. Phosphonyl chemistry. That's weird. And now you form a not an acid chloride, but a phosphorus acid chloride. Wow, this seems like an extremely annoying route. So this is a disubstituted benzaldehyde. So 3-methoxy-4-hydroxybenzaldehyde. This is an amide here, and this is a carboxylic acid. Wait. Oh, Act 2O. I just learned about this. This is acetic anhydride. I learned about this literally today, that I should know that Act2O means acetic anhydride. Holy shit. Dude, does this not seem like overkill? That's insane. Well, 1,000 people synthesize this. Here's Soutine. Is that it? Tricyclic, weird fucking thing. This looks different. Okay. I don't really know what this is. Can we get the DOI? Dude, I really gotta learn how to name these bicyclic fucking things. Alright, we're almost done with this part of it. We'll get on to real chemistry in a minute. Oh, wait. Ibogamine. Is that the same as ibogaine? I think this is the same as ibogaine. I think they just renamed it. Okay. What the? What the? Hey, Peter. Hey, Peter. So you start with, oh geez, not the acrolein. Oh wow, but actually this is cool. Acrolein is not only really good at doing Michael additions, but it can also be used for Diels-Alder. That's pretty cool. Acrolein seems like a very useful molecule. I think we went over something about this trifluoroboron thing, but I don't know anything about that. So this is just there's got to be a name for this. indole with the two. Oh, okay, that's tryptamine. So then tryptophan just has the CO2H on it. All right, that's pretty neat. Jamtine, not identical to natural jamtine. It's stuff like this that makes you realize just how much effort has gone into the program of organic chemistry. Like, wow. Yo, these guys went dang hard, man. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19 steps used in part 2. Des Martin is I think Des Martin might be an oxidizer, right? So it'll take like an alcohol to a ketone or something? Ooh, pinene. All these terpenes I want to make because they smell nice. Alright, well, we got to go through this one. I'm not even going to say the name of it, so don't even get me to say it. Mannose, I think that's a sugar. Alright, let's look at this. So we have. Oh, interesting. This isn't even indole here. But we have. Oh, shoot. Friedel Crafts acylation. I completely forgot how Friedel Crafts works. Hey, Peter. Oh, well, first you form an acid chloride. And then aluminum trichloride. I don't know why that bromine gas would put a Br there. Oh, but here, this is one of those ethylene it's not ethylene glycol, but it's like there's some weird name. Actually, it might be ethylene glycol. Oh yeah, okay, that's ethylene glycol. So, but I have to remember this reaction. I don't remember like you do this weird thing to protect a carbonyl. I think I low key forgot everything from last quarter. Evidently. Dude, Woodward! Come on, man. This guy is in everything, bro. Kornfeld, too, I think. Dude, these guys are. These guys are goated, man. Dude, we've been studying Woodward stuff for like. Oh wait, didn't we already do these morphine ones? I let's see. Is okay. Come on, I'm trying to finish this. I just want to look through. Ooh, I was actually curious about the synthesis of this. This is a leaving group. What is a PIV? What the hell is a PIV? N-butyl lithium. I don't even know what this is. But oh, you know what this is though? This is an intramolecular ester. So we can actually open this ester up. That's what happens. So, so I'm not sure how, but nucleophilic attack from here comes into here. In, up, down, out. Then you have this, and then somehow it takes a proton from somewhere. You know, I don't know what this is. COCl2, I don't know what that is. Triethylamine. All right, fine. So for somehow they turn a primary alcohol into an aldehyde. I'm fine with that. What's a PIV-O? Pivyloyal oxy group? Okay, so it's just yeah, all right, this is what I want to know. So okay. Pivylic acid. All right. So pivyloyal oxy group. Oh, okay, pivyloyal oxy. It actually all makes sense. That's not so bad. All right, so pivyloyal oxy groups and all of this. So we have this cyclohexane ring that's substituted to all hell. Oh, but it's actually not cyclohexane because it's got. I think we're gonna do more heterocycle chemistry later in the quarter. I don't know what this borohydride with the cyanide ion is. So somehow we get a ring closure here. That's kind of cool. Wait, actually, no, wait, hold on. Well, it ring closes, but it ring closes. So this lone pair substitutes for this oxygen. H minus attack from the top reduces the iminium ion. So here's the iminium ion. And then acid in methanol. How does this work? You have H plus floating around. I don't really know how that last step works, but this is a pretty cool one because I could actually understand almost everything except for like, I don't really know what this N-butyl lithium thing is. I don't really understand what this Actually, I think I. But why is the 2 there? I don't really get why the 2 is there. And then this. Is this just acetic acid? That's got to be acetic acid. See, you gotta get. I think a big part of this is just getting good at the name the shorthands. But I feel like I could do this, like kind of. I love carbonyl chemistry. Carbonyl chemistry is like actually amazing. It's so versatile. Nutkaton. Bro, me and the homies about to go do some nutkaton. Bro, don't mess with me, man. I'll bring out the nutkaton. Oh, Pinatol? Wait, I've heard of this. Wait, no, I'm thinking of Pinacol. I'm thinking of. What is this again? Pinacolone. Oh, so this is kind of like. Wait. Wait, the fitting reaction? So there's a fitting and a witting. Alright. You my fitting to my witting. My. Alright, Alright, so pinene. I've always wanted to make pinene. This. Let's see if. Hagman's ester? Okay, so wait. First thing we should see, we got this alpha beta unsaturated ketone here. And then we have a methyl ester on this cyclohexene thing. Alright, so what the hell is going on here? Oh, wow. Is there any reason they had to do this instead of just like ethylene glycol? That's pretty cool. Is it because LAH reduces ethers or something like that? I don't think LAH reduces ethers. I wonder if it would work if you did ethylene glycol. What's the real name for it? Just like 1,2-ethane diol? Yeah, it doesn't flow off the tongue as well as ethylene glycol. But ethene diol, actually, you could just no, you have to say 1,2-ethene diol, but or wait, ethane diol. All right, so here we have AC2O. This is acetic anhydride and pyrimidine. Oh, so the alcohol, dude. See, carbonyl chemistry is all over this thing, man. Like literally, most of the OChem that I've seen in this thing is from this quarter. So, all right. So you have acetic anhydride. In, up, down, out. And so now we have introduced Yeah, so this is a yeah, acetate group. Okay. So I get this kind of this is amazing to me that there's an analogous thing for a one two ethane dithiol or something like that. I would love to know what the real name of that is. All right, so let me see. What's the name for 1,2 ethane dithiol? Where instead of like ethylene glycol, it's thiol groups with sulfur. Dude, I also want to try out the new voice thing. How do I do the? I think it might be only on my phone. Ethane dithiol. 1,2 ethane dithiol. That is pretty cool, dude. It's often used to convert aldehydes or ketones into cyclic dithioacetyls, specifically five-membered rings. One, three, yeah. So this is 1, 2, 3, 4, 5. Okay, all right. Mercury chloride. There must be a reason why they need to do that. Okay, but fine. You return the dithiol back to its ketone, and the reason for that is presumably there's a conflict. See, I actually wish they would. Like, I know that. I mean, like, this is a good step to higher level synthesis. Because, like, reagents are one thing. Okay, fine. The reagents do things. But, obviously naming the graph rewrite rule, that's good. That's a good thing. But then, at some point, you want to write patterns of rules. Protect, deprotect. I like writing it as a more high level program that can be compiled. Dude, people must be thinking about this. I'm not the only asshole that thinks about this stuff. So it's just like we're in a society that's not like up to speed with like computers, man. Whatever. Maybe it's not even valuable. Okay, so here, ooh, we have one of these organocuprate things. And what does an organocuprate do? I thought an organocuprate, uh, yeah, I thought organocuprate took an acid chloride and made a ketone. It must be used for something else. I would need to know the mechanism, because obviously there's a positive charge here, right? Is phenyl CHO, is that just benzaldehyde? Not to brag or anything, but I actually think I could be pretty good at chemistry. If I locked in, I could be a pretty good chemist, I think. Because I like it, you know? Like, I kind of like this stuff. But it also feels like, it's like memorization. Like, it's not... It just... Organic chemistry can only take you so far, I think. Okay, so what the fuck is happening here? I have no idea how this works. We have this... What do we call this? Methyl cyanide? Oh, acetonitrile. Yeah, I forgot about this, which I would call... The systematic name is ethane nitrile. Yeah, ethane nitrile. So this thing is a good leaving group. This is a base. This is an alpha proton. Maybe we can pull off this proton and you know, if we look at this resonance structure, right? Like all right, base, boom, boom, boom. Here we have the enol minus charge here, or no, not a minus. The enol. So there's probably some minus charge here. An aldol to an enone. Oh, and look, here we have another one of these. Alpha beta unsaturated ketone. Okay, so we protect our alcohol. We add NaH. And let's see. What do you call this? These diester or diether? Methyl 1,2 di. What do you call this? What do you call this? Oh wait, hold on. Guys, I'm busy. All right. More chemistry. All right. So I don't know what's happening here. This name is 1,2-dimethoxyethane. Okay. Oh, that makes sense. Yeah, 1,2-dimethoxyethane. And it's also called Glyme. She glime on my rhymes. That's pretty cool. We call this shit Glyme, brother. So, but I want to know how the hell this thing happens. This is an acidic proton. And if I had to pick the next acidic proton, it would probably be this. There's no proton here, but there is a proton here, and I would assume, because if you draw this resonance form, that there's positive charge character here. So my feeling would be that the bridge would try to occur across here, but I don't know why. Ketone enolate. So yeah, okay. First thing, there's a minus charge here. Can you attack an ester or an ether like that though? Wittig. All right, I gotta review my Wittigs. I don't know that one, and I don't really know what's going on here too. Retroaldol. Okay, but I actually worked my way through a lot of this just in my head. I would prefer to like draw a curved arrow mechanism, but this stuff is awesome, dude. I can't believe I didn't know about this website, man. This website, because the thing is, I was begging chat. I was like, please give me synthesis problems that aren't just like one step, because they're so boring that way. You have like no idea how boring. Like it's like, okay, add the thing. This one I need to review because this one is apparently we're able to cover most of the Woodward reserpine synthesis. Dude, Woodward actually was so sick. Dude, Woodward is the overall GOAT. Woodward transformed total synthesis from clever reaction picking into something resembling a coherent intellectual R. His landmark syntheses are quinine, cholesterol, cortisone, strychnine, reserpine, chlorophyll. Dude. Vitamin B12. E.J. Corey. Corey formalized retrosynthetic analysis. Stork is also apparently here. Dude, so Woodward is the GOAT. It's not just like Woodward really is the GOAT. That's pretty sick, man. Wait, tetracycline. I feel like I looked at. Oh, wow. Ryan Odall. Dude, I can't believe they synthesized strychnine. That seems sketchy as heck. Because isn't that like the most potent poison? I'm pretty sure that this is just like not good for you. So see, biosynthesis to just have like pretty easy. Wow, it starts from tryptamine? Really? Glyme? Are there interviews with Woodward? I mean, he got the Nobel Prize. Presumably there's some video. Is there sound? Please tell me there's sound.
Gives a talk, he's not introduced. But let me dispel any illusions you may have. I'm not Woodward. I decided that it's time the vision of Harvard changed slightly, and that maybe this would be a good opportunity to continue the tradition that we have started in this year's organic. To be told, the practical foresight side would more nearly resemble one of those delightful Japanese verses that they do, I think, with a few syllables. Then the census slide and be rather a lot more complicated and take longer. And so one has to make choice. If we're to get away from here. I was going to say at a reasonable time, you're not going to get away at a reasonable time. But let's say in a relatively short time. Now, such close collaboration, in which even samples were sent back and forth, reactions were started in one city and finished in the other. It was a very, very close, fruitful, cordial, indeed extremely pleasant collaboration. And it's a very great privilege for me tonight here to be able to be the spokesman for both of these groups. The group Zurich, associated with Professor Eschenhauser, and the group here in Cambridge, loosely associated with myself. Now, let's slide. And we need some focusing. That's pretty good, Odin. A bit better. And perhaps
Dude, they made that? Dude, what? Wait, is this attached to... Hold on. Please 3D. Please give me 3D. Look at that name! Oh my lord. They only have 2D structure of this? Oh no, it is connected.
present a challenge and an opportunity to the chemist to test the principles that he knew and perhaps develop new ones. Much of the interest in this problem devolved from the stereochemical content, its stereochemical content.
These video clips are glazed in a nostalgia that bites the thought that maybe Woodward's noble obsession, like smoking a lecture hall, is a hallmark of a bygone era. It's an alluring thought, but one that we think is false. His passion still permeates chemistry. Now, there's absolutely something special about seeing Woodward through the lens of a 40-year-old camera. But some of that is reminders that still hold up today, like with this room in chemistry portability.
Now, altogether, over a period of 11 years, Professor Eschenmoser and I had 99 associates in this work. And they are, of course, the people who actually accomplished the synthesis. And it is to their credit, very much so. They're a very devoted and skillful group of people. I've described reactions very casually as though they just could be carried out by pouring things from one bottle to another, but in almost every case, the reactions I described had to be carried out under extremely carefully defined and prescribed conditions with all sorts of special precautions. I may say also that much of the work which was done in exploring the ways to find the routes which were ultimately discovered was done on a very small scale, on the order of 50 micrograms or so. When you're 75 steps away from home, you don't want to use up much material each experiment. And you may have to do hundreds of experiments or even thousands. And so you use very small quantities of material. And when you want to exclude absolutely rigorously oxygen or moisture from a reaction on the 50 microgram scale, that's a chemist that can do that.
These old videos are magical. And don't take our word for it. You can watch them in their entirety on Thomas Hoy's website. We owe a huge thanks to Hoy, who is a professor of chemistry at the University of Minnesota. He shared this with us, and we also need to thank Professor Madison Hall of Cornell College and Iowa for making the footage available. If you want to stay up to date with all things chemistry, click on our red logo and subscribe.
Dude, Woodward, bro. Oh yeah, and then Jansen though. Yeah, dude, Paul Jansen too. Okay, enough. But I gotta see the vitamin B12 synthesis. What? Presumably, this is the paper that won them. Is this an IR? What is that? Isn't it under a different name though? Isn't there's another name? But presumably it would, if it was in there, be under the um. All right, well, whatever, man. How many how many steps was the total synthesis that Woodward performed for vitamin B12? I can't find like a diagram online or a map that explains it, all the steps. Dude, that's insane. It took him 12 years to make vitamin B12. Like, it took them 12 years to make vitamin B12. Okay, I found it on Sin Archive. You gotta be kidding me. So you start out with just two butanone. Yeah, and then you have wait, what the hell is that? Wait, that's a weird molecule. Dude, what is this? Two oxo. So oxo is when you have an. Oh yeah, oxo is when you have a ketone. Two oxoacetic acid. Okay. We have a Claisen condensation. All right, all right, all right. It's time to stop fucking around. It's time to get onto it. Had my fun, but it's time to get back to business. All right, so yeah, so this is pretty easy. I'm gonna review this just like briefly, then maybe do some problems in the back of the chapter because I think that this stuff is not that bad. Okay. Okay. All right, so this is a carbonyl. Let's say we take off this proton from this double bond and kick a charge onto here. This would be an enolate. And an enolate has a resonance form where this lone pair goes down and then a negative charge goes on here. Okay, so let me just. Okay, so we have a carbonyl. So we have an enol, a carbonyl, an enolate, and then its resonance form. Okay, the tautomerization mechanism. Here we go. So the acid catalyzed. Okay, so Okay, so I'm gonna just try to. So I'm going to try to predict what the. Okay, so the acid catalyzed enol tautomerization makes sense. So now this next part is going to be the base catalyzed. And I think that this one might be easier. All right. So this one's pretty simple, I think. Right. I mean, I guess we could draw this resonance form here. Actually, wait, what is the resonance form here? Oh, yeah. For some reason, this resonance form is weird to me. Because, like, the plus doesn't move over this, it moves over this. But all right, so the base and acid catalyzed tautomerization is all good. I think I did this one. Okay, so then the reactivity of enols in substitution reactions. Um, but because of the resonance electron donation of a lone pair of electrons on the neighboring oxygen, enols are more electron rich and correspondingly more reactive than alkenes. Okay, so enols are more reactive than alkenes. When an alkene reacts with an electrophile, initial addition gives an intermediate carbocation, and subsequent reaction with a nucleophile, such as a halide ion, yields an addition product. When an enol reacts with an electrophile, however, only the initial addition step is the same. Instead of reacting with a nucleophile to give an addition product, the intermediate cation loses the OH proton. All right. So even if I already did this, it's the fundamentals that matter. All right, so we have a carbonyl alpha sub reaction general mechanism. All right, so we have a carbonyl with an H, with a hydrogen, and we have acid. So proton takes, now we have a protonated carbonyl. Okay, so now we want to form the enol, right? Okay, now I see the minus. So for me, the exercise is basically, you start with a carbonyl, you form the enol, you show both resonance forms of the enol, and you find that there's a negative charge on the alpha carbon, which can then come in and attack an electrophile. Yeah, the other way that you can draw this is you have the enol. But I think I like the explicitness of showing the negative charge character on the alpha carbon. But I mean, it's whatever. I never drew this cation. But alternatively, one you could have. You could also do this. Okay, so that's pretty good. This is the general mechanism of alpha substitution on a carbonyl. All right, alpha halogenation of aldehydes and ketones. Bromoacetophenone. A particularly common alpha substitution reaction in the lab is the halogenation of aldehydes and ketones at their alpha positions by reaction with chlorine, bromine, and iodine in acid. Do we get a mechanism? Okay, cool. Okay, so I'm guessing the first step is kind of form an enol. So here's the enol. And then swing, swing, ba-boom. Okay. Okay, so practicing it again. Um, I'm gonna see if this pisses me off today. I feel like I don't want to do. You know what? I don't actually care. Paper and pen is more fun. The iPad just kind of sucks. Okay, so we have the alkene now, and now here's what happens. And we can just draw this directly to Br. This seems impossible. This seems impossible because if there's zero halogen, then no halogenation can happen. I guess it's not rate limiting. Okay. Okay, alpha bromination of carboxylic acids. All right, so we did ketone, and let's also do. When talking about carbonyl chemistry, the carbonyl carbon is called what? I know that the one next to it is called alpha and then beta and so on, but what is the carbonyl carbon itself called? I think that's so dumb, man. Yeah, whatever. I don't care. Okay, so this was 22.3. Alpha brom of carboxylic acid. The alpha bromination of carbonyl compounds by Br2 in acetic acid is limited to aldehydes and ketones because acids, esters, and amides don't enolize to a sufficient extent. What is the mechanism there? Uh, oh, here we go. Okay. Damn it, it's so freaking annoying. There we go. It's just like the sulfonyl chloride. It's like you've made this thing that is a good leaving group. Okay, so we have the acid bromide. I'm okay with that. Okay, so I have the enol. Okay, now I'm here. Oh, now we hydrolyze. Or wait, actually. All right. That's pretty neat. All right, now 22.5 acidity of the alpha hydrogen atoms, enolate ion formation. So there's a 10 to the 40 factor difference in the acidity of these ketone alpha protons versus just ethane's protons. So alpha acidity, 22.5. So LDA is lithium diisopropyl amide. See, wait. Okay, hold on. Is amide an overloaded term? Because amide can specify that there's an amine group on the alpha position of a carbonyl. But also it can refer to just an amine ion, I think, right? Bro, that's actually really annoying. Yeah, context makes the meaning clear, but it's still an overloaded term. Because this is not an amide, amide, whatever, with a carbonyl there. It's just an amide ion. Diisopropyl. Okay, so if we have cyclohexanone, LDA, THF, then these. So the alpha proton of a ketone has a pKa. Isn't there a pKa table? Oh, perfect. So ketone is like 19. Okay, so we have the enolate. So this is an enol 8 because it's an ion. And we have the resonance forms of the thing where there's a minus charge here and there's the carbonyl here. Oh, and one thing I guess we do see that there's lithium around. Okay, so there's lithium around. Big fucking whoop. Okay, this is the thing to remember though. So really, like memorizing this pKa stuff is actually so helpful. Many types of carbonyl compounds, including aldehydes, ketones, esters, thioesters, acids, and amides, can be converted into enolate ions by reaction with LDA. Table 22.1 lists the approximate pKa values for different types of carbonyl compounds and shows how these values compare to other acidic substances we've seen. So LDA help me understand the logic behind comparing the pKa's to understand what happens basically. So the proton in that carboxylic acid has a pKa of 5, meaning it's pretty strong. And the pKa of what I believe is the conjugate acid of LDA has a pKa of 36, meaning it's weaker. And because it's weaker, the diisopropylamine will be protonated by the carboxylic acid because its conjugate base is so strong. So, is that right? Yeah, right, because this is acting as an acid, donating up this hydrogen. But it really doesn't want to give up this hydrogen. But this thing really wants that hydrogen. Okay, got it. There's a lot of like flip flops in. I mean, one thing is just that you're taking the negative log, so you need to remember that the lower the pKa, the stronger the acid. But whatever. I mean, at that, it's not that hard. So here we go. So the next best thing is these 1,3 diketones, so the beta diketone, because these protons, and I'm just going to draw this out. We get this 1,3 diketone. What I'm going to do is just say that this has a pKa of 9. These are pretty strong, and And so if we take this off with a base, bam, bam. And we can delocalize it over a pretty big amount of stuff. We can delocalize it over both carbonyls. It's very stable. Okay, now if we do a diketo or a 3-keto ester, then these protons pKa is probably like 11. Now 1,3 diester. Oh, that's interesting. The acid chloride protons are about as strong as the alcohol protons. Wait, is this a nitrile? I think that is this a bug, bro? I think this is drawn wrong. I think this is drawn wrong. I think nitrile, there should be a triple bond between that second carbon and the nitrogen atom. What? It didn't fucking what? No, but I think that's drawn wrong because the picture has a double bond between the carbon and the nitrogen, but it should be a triple, right? You gotta be careful. This book has some bugs in it, man. All right, whatever. So for an ester, looking in detail at this table is helpful. Wait, I just jumped too far. All right, nice. Enolate ions are more useful than enols for two reasons. Pure enols can't normally be isolated but are instead generated only as short-lived intermediates in low concentration. I think there was some exceptions to that too, where actually the enol was more stable, but I can't remember what they were. By contrast, stable solutions of pure enolate ions are easily prepared from most carbonyl compounds by reaction with a strong base. Second, enolate ions are more reactive than enols. And undergo many reactions that enols don't. Whereas enols are neutral, enolate ions are negatively charged, making them much better nucleophiles. Yeah, okay, it's starting to come back to me. Because they are resonance hybrids of two non-equivalent forms, enolate ions can be looked at either as vinylic alkoxides, C double C single O minus, or alpha ketocarbanions. Thus, enolate ions can react with electrophiles either on oxygen or on carbon. Reaction on oxygen yields an enol derivative, while reaction on carbon yields an alpha-substituted carbonyl compound. Both kinds of reactivity are known, but reaction on carbon is more common. The fuck did you just say to me? The fuck did you just say to me, bro? Dude, this is my fucking town. What the fuck did you just say to me? You fucking hoser? What the fuck did you just say to me? Alright, back to work. An example of an enolate ion reactivity. Aldehydes and ketones undergo base-promoted alpha halogenation. Even relatively weak bases such as hydroxide ion are effective for halogenation because it's not necessary to convert the ketone completely. Into its enolate ion. As soon as a small amount of enolate is generated, halogen reacts immediately, removing it from the reaction and driving the equilibrium further towards enolate. Base-promoted halogenation of aldehydes and ketones is seldom used in practice because it's difficult to stop the reaction at the monosubstituted product. An alpha-halogenated ketone is generally more acidic than the starting unsubstituted ketone because of the electron withdrawing inductive effect of the halogen. Thus, monohalogenated products are themselves rapidly turned into enolate ions and further halogenated. If excess base and halogen are used, a methyl ketone is triply halogenated and then cleaved by base. Yeah, but it's a cool way to make tribromomethane. What is this? What does it look like? It's organic chemistry. Okay. All right. So that was pretty straightforward. They just make a statement about enolate reactivity as being more than enolates more reactive than enols. And then there's also an equilibrium driving force. Because as you remove it, then the equilibrium keeps going, and so you can make a lot of it. Probably not like a ton of it, but you can make a good amount of it, I think. Actually, You might be able to make all of it. I don't know. All right. Alkylation of enolate ions. Perhaps the most useful reaction of enolate ions is their alkylation by treatment with an alkyl halide, thereby forming new carbon-carbon bond and joining two smaller pieces into one larger molecule. Alkylation occurs when the nucleophilic enolate ion reacts with the electrophilic alkyl halide in an SN2 reaction and displaces the leaving group by backside attack. All right, so why do they draw it with three things here, though? So this is just like a... All right, so sterics matter. But so let's just do this. Actually, where did Nick Lane teach? Oh yeah, I was right. UCL. All right, cool. Alkylation reactions are hold on. Alkylation reactions are subject to the same constraints that affect all SN2 reactions. Okay, yeah, obviously. One of the oldest and best known carbonyl alkylation reactions is the malonic ester synthesis. A method for preparing a carboxylic acid from an alkyl halide. Okay, so this is an RX to... Now, the important part here is, now this is a crucial part. But then we have an enol, and the enol tautomerizes. Heat and acid is necessary for the decarboxylation. I'm just gonna go through quickly in ester hydrolysis, just so that I'm like, bam. I mean, at this point, it is like so second nature to do these Fisher esterifications and hydrolysis. Hydrolyzed is such a cool sounding word, by the way. Okay, so I'm up to here. Decarboxylation is not a general reaction of carboxylic acids. Rather, it is unique to compounds that have a second carbonyl group 2 atoms away from the CO2H. That is, only substituted malonic acids and beta keto acids Yeah, where's a beta keto acid? So beta keto acid is probably the more general form. This is the one that I would prefer to look at. Because it's like, okay, malonic acid. Yeah, it's... I mean, the malonic acid thing is actually pretty general too, but... But whatever. I don't know why they show this. They just show this because... A malonic ester synthesis can also be used to prepare cycloalkane carboxylic acids. Oh, this is where it was this morning, and I was trying to read this in class. For example, when a 1,4-dibromobutane is treated with diethyl malonate in the presence of 2 equivalents of sodium methoxide base. Okay, wait. 1,4-dibromobutane. So is treated with diethyl malonate. So diethyl malonate is another way to say um, how would I say this? Diethyl propane dioate. Yeah, see this. Yeah, like ethyl acetate, ethyl diacetate, ethyl ac. I think you would have to say ethyl ethane ethane dioate. Ethyl ethane dioate. Is that even possible? Or diethyl ethane dioate? You know. What is going on? Aye, aye, aye. Um, Okay, so wait, I want to go through this because this seems really cool. So we have a minus here. And this minus is going to alkylate. Okay, so now we're going to do this. Oh. Oh wait, but this gets hydrolyzed too. These seem pretty good. Usually, I haven't been really doing many problems, but these seem pretty good. See, how long have we been going here? What is it? 2:30? Wait. Which chapter is 22? All right. Acetoacetic ester synthesis? Oh, right. And then this one's not going to leave. Okay, I think I can skip this. I get that. That's not that much of a jump to me. I think there's a lot more material that needs to happen. But that is very cool. I don't get what this means. Alternatively, however, it's possible in many cases to directly alkylate the alpha position of monocarbonyl compound. A strong sterically hindered base such as LDA is needed so that uh, complete conversion to the enolate ion takes place rather than a nucleophilic addition. I don't understand the requirement of the complete conversion to enolate needs to take place rather than nucleophilic addition. I don't know what that means. Wait, I don't remember this. Dehydrobromination? I don't remember them talking about this. Okay. So for space repetition, I'll probably just uh I mean I should probably do some of these problems, but I will do it later. Tomorrow morning or something. Because we gotta get through aldol, Claisen, and Michael. Oh, and Robinson annulation. Yeah, all this stuff is gonna be sick. You know, I'm so excited. I'm gonna get some water. But all right, let me read the intro and then I'll get some water. All right, so the chapter is Carbonyl condensation reactions. Actually, you know what? I'm gonna restart this. No, I'm not. I'll just change the title later. All right, we'll see in this chapter and again in chapter 29 that carbonyl condensation reactions occur in a large number of metabolic pathways. In fact, almost all classes of biomolecules, carbohydrates, lipids, proteins, nucleic acids, and many others, are biosynthesized through pathways that involve carbonyl condensation reactions. As with the alpha substitution reaction discussed in the previous chapter, the great value of carbonyl condensations is that they are one of the few general methods for forming C-C bonds, thereby making it possible to build larger molecules from smaller precursors. In this chapter, we'll see how and why these reactions occur. We've now studied 3 of the 4 general kinds of carbonyl group reactions and have seen 2 general kinds of behavior. In nucleophilic addition and nucleophilic acyl substitution reactions, a carbonyl compound behaves as an electrophile when an electron-rich reagent adds to it. In alpha substitution reactions, however, a carbonyl compound behaves as a nucleophile when it is converted into its enol or enolate ion. In the carbonyl condensation reactions that we'll study in this chapter, the carbonyl compound behaves both as an electrophile and as a nucleophile. Oh, this is so sick. This is when. Oh, this is a general mechanism of carbonyl condensation. Okay, cool. Yeah, I gotta get some more water. Damn, I'm kind of bummed that like if I switch to physics, I won't get to take the biochem sequence. There's like 3 classes of biochem, and it's like I would love to take 3/4 of biochem. Like I really like those long sequence classes where you're really building knowledge. Like here and there classes, it's like so much is lost. I don't know. Even just like if you have a sequence class and like for instance my organic chemistry, I had one professor for the first class, a different professor for the second class, and then the same professor as the first for right now. And I wish I had him for all three because that would have been like it would have been just so much more coherent. I feel like I'd be way more ahead of where I am now. Cause like the way that we handle like ring stuff, like even this, like yeah, I went through the mechanisms, but I wasn't challenged in the same way as the professor that I have now. This stuff, chapter 16, chapter 15, polycyclics. Oh, and then I think 31, right? Not 31. Oh, 30. Yeah, pericyclic stuff. I wonder why they say that for the end, because I feel like you really can't understand stuff like a Diels-Alder unless you have some sort of understanding of uh, the nature of polycyclic reactions. But like, I don't even know that much about them. Like, I barely did any problems from them. Like, truth be told, I really can't say anything about my understanding of like benzene rings and this benzene stuff. Like I literally crammed it before the exam and now I don't even know it. So that was kind of an L actually. This whole 15, 16. I don't know anything about phenol. I think we kind of skipped phenol. I don't remember doing anything with that. Ethers and epoxides. That didn't seem that fundamental either. Maybe it was because I think we might have even. I don't even remember when we learned that. Wig. Even this. I mean, basically the whole last quarter, I was not keyed in. I was taking 4 classes. That's a big reason why. But that's why I'm so excited now. I'm just like, and I've been off my game too. Like, but I'm back on. Like the next couple weeks, dude. There's so many family engagements. It's so annoying. I haven't had any time for projects, but I do just want to like get really good at chem because like it's just so interesting. You know that you can make stuff. Okay, let me get water. All right. I need to get some salt. Actually, Loki, I'm just gonna eat downstairs. It's gonna take me like 5 minutes. More chemistry. Ah. Okay. I feel like this is gonna be a long chapter. Yeah. Alright, the fucking SpongeBob hat comes back on. This is the lock-in hat now. Alright. So alright, carbonyl condensation reactions take place between two carbonyl partners and involve a combination of nucleophilic addition and alpha substitution steps. One partner is converted into an enolate ion nucleophile and adds to the electrophilic carbonyl group of the second partner. In doing so, the nucleophilic partner undergoes an alpha substitution reaction. Wait, actually, I probably need to turn on my rank. Oh, yes. Yeah. Okay. Hold on. I have to go do something. Someone. Okay. All right. Um. All right. Let's just look at the mechanism. Sometimes I just get so stuck on reading it that I can't just look at the mechanism. All right. So here's the general mech of carbonyl condensation. All right. So we have Okay, so aldehydes and ketones with an alpha hydrogen atom undergo a base catalyzed carbonyl condensation reaction called the aldol. For example, treatment of acetaldehyde with a base such as sodium ethoxide in a product solvent leads to rapid and reversible formation of 3-hydroxybutanol, known commonly as aldol. All right. The exact position of the aldol equilibrium depends both on reaction conditions and on substrate structure. So this gets taken, en minus comes back down, this pi then All right, so it's catalyzed by base. So we're allowed to assume that base does it. So the important part is definitely going to be practicing mapping carbons. Okay, I got it right. But actually, I feel like this thing might be better here. That's still drawn like shit. Wait. Oh. Yeah. Wait. 1, 2, 3. Oh yeah, because 1, 2, 3. See, this is why you gotta get good at mapping these carbons, man. So phenyl, carbonyl. This is that carbon, this is this carbon, and then finally this would be O minus methyl phenyl. Okay, that's right. Okay. Oh fuck. Okay, that's kind of what I drew. It looks weird. Okay, I do want to understand the reverse aldol. Using curved arrows to indicate the electron flow in each step, show how the base catalyzed the reverse aldol reaction of 4-hydroxy 4-methyl 2-pentanone. Okay, so let's figure that out. So 23, 2. So we got pentanone. We got 2-pentanone, 4-hydroxy, 4-methyl. It takes place to yield 2 equivalents of acetone. Okay, so I'm just going to do this how I know. So first, I'm going to do the forward aldol because I know the product. It's harder when they don't give it to you, so that's okay. So O minus alkene swings back down, attacks. So now we're going to get The reverse aldol is freaking weird, man. I think the thing that's weird about the reverse aldol is the fact that a carbon carbon, yeah, like that just seems weird that a carbon carbon sigma bond is breaking. Mhm. Okay, reverse aldol. Not that bad. Not that bad. I think it'd be much harder if they don't provide you what the starting is, or what the what did the aldol. Yeah, this is actually a good point. Two of the four general carbonyl group reactions, carbonyl condensations and alpha substitutions, take place under basic conditions and involve enolate ion intermediates. Because the experimental conditions for the two reactions are similar, how can we predict which will occur in a given case? When we generate an enolate ion with the intention of carrying out an alpha alkylation, how can we be sure that a carbonyl condensation reaction won't occur instead? Alpha substitution reactions require a full equivalent of strong base and are normally carried out so that the carbonyl compound When heated under the acidic and basic conditions, the beta hydroxyaldehydes or ketones. Yeah, the beta hydroxyaldehydes or ketones formed in aldol reactions can be dehydrated. Oh, just by an E2 to yield an alpha beta unsaturated product. Or conjugated enone. Right, okay. Conjugated enone. That's another way to say the alpha beta unsaturated ketone. The conjugated enone. In fact, this loss of water that gives carbonyl condensation its name, because water condenses out when an enone product forms. Most alcohols are resistant to dehydration by base because hydroxide ion is a poor leaving group, but aldol products dehydrate easily because they're carbonyl group. Under basic conditions, an acidic alpha proton is removed, yielding. Wait, hold on. I gotta see this. All right, so here we have the. So this goes here, 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 here. Okay, but the acid catalyzed is pretty much always protonate the, or actually protonate this, protonate this. They both protonate. This would probably protonate. I actually don't know. Like, will the ketone or carbonyl or the alcohol group protonate more easily? Or is it the same? The alcohol oxygen generally protonates more readily than the ketone. It's insane to me that you really got to understand these pKa's because the protonated ketone has a pKa of -7. So it's really strong. But okay, fine. This protonates OH2. This also protonates, fine. I actually have no idea what they're trying to say here. Like, where does this enol... How does the enol even form? I think it's that the conjugate base of the acid takes that alpha proton. Okay, and then what happens is this either, B comes in, takes this hydrogen, swings down, and then kicks off this OH2 group, which leaves as water. So then you get the conjugated enone. Okay. Um. Okay, so formation or condensation of the what do we call the aldol product? The beta hydroxyketone. The aldol product, which is the beta hydroxyketone carbonyl or carbonyl. Is acid or base, and acid and base catalyzed. Okay, so let's see if I can do this from memory. So we're going to start off with a beta hydroxy then we're doing base. Yeah, and then that's a Crolian. I mean, the way I drew it. So I wonder if I can synthesize a Crolian with an aldol reaction. So let me think about it, because that would be a good actually. So okay, wait, this is the base one. Let's see the acid one, and then I'm gonna do a synthesis of a Crolian. Trying to do it with the aldol, because I'm trying to see how this thing works. All right, so we have this. Oh wait, what the fuck? No. This is all fucked up. Okay, now I got it. Okay, there's the acrolein. I think that acrolein stuff is hella toxic. All right. All right. So I'm trying to synthesize it with a. So I'm gonna start with formaldehyde, which I should really say is methanol. So we're gonna start with methanol, and what I'm gonna do. Oh, but methanol. Okay, no. I'm gonna start with ethanol, which is, what is it actually called? Oh, acetaldehyde. Okay, I'm gonna take acetaldehyde. All right, and then I'm gonna take a proton. To form my enolate. My enolate. So now I have my enolate ion. And I also have my original acetaldehyde. What I'm going to do is I'm going to swing these electrons down and then come and attack this. So then I'm going to have O. I actually don't think that I... Oh, but you have a crossed aldol. So if I had a mixture, I mean, you don't want to do it because it's pretty dumb because you're just like, it's a bad idea, but you could do it. And so what I could do, okay, but now what I want to do is I want to do the condensation. So now, so wait, hold on, let me, 1, 2, 3, 4, 1, 2, 3, 4. So this is right. And I'm going to add base. Okay, now we have an enolate here. No, actually, doesn't it just... Don't we just do this? I'm pretty sure we just do that. It just directly does an E2. It's not like a crazy fucking whatever. But so this is not going to be a Crolian. This is going to be like 2... Or this is going to be But 2 en al. Enal. 2 butene al. But 2 enal is a systematic name for crotonaldehyde. Oh yeah, you actually have an EZ thing, so I'd have to say E2 butanal. This stuff is probably pretty toxic too, I bet. Just because it's so reactive. It says it's not very toxic. I wonder why it's not that toxic. It says it has a suffocating odor though. So Wikipedia at least says it stinks. Oh, it makes you cry too. Huh. Okay, so So wait, let me look up the. Okay, so it seems to me that if I want to avoid doing a crossed aldol reaction, then there isn't really a way to make acrolein from an aldol unless you do it as a cross between two different things. Is that correct? Because I tried to do the simplest aldol, which would presumably be acetaldehyde, and I got that butene-al, or the crotonaldehyde. Ooh, dude, did chat's transcription actually good? It's actually good, man. It's like better than I would expect. Self-aldol condensation of acetaldehyde cannot give acrolein because two acetaldehydes combined give 4 carbons. Yes, okay. Oh, interesting. Actually, because formaldehyde has no alpha, you could do the crossed. So let's try that. I want to try that. Okay, so we have formaldehyde in the flask, and we've got acetaldehyde in the flask, and we're trying to make acrolein. So, and we got base, formaldehyde, no alpha proton. So then we basically just can take this. Nice. Okay, so I think literally the only thing that could also happen though is that um this could also, so the two products that we can make, we'll get a mixture of this and crotonaldehyde. So if I did the crossed aldol reaction with formaldehyde and acetaldehyde, then I would get two products. I would get acrolein and I would get crotonaldehyde. But the thing is, can't it like polymerize? All right, that was a fun exercise. All right, so yeah, enones. Hold on, the base catalyzed one. No, yeah, see, they do draw it with an analyte intermediate. So instead of just doing it as an E2, you really want to draw. So I got to get this down. All right, so we have this thing. It's literally just one extra step, but I don't know why I was tripping. All right, all right. I did these one last time. That's then I'm done. The reaction conditions needed for aldol dehydration are often only a bit more vigorous, slightly higher temperature, for instance, than the conditions needed for the aldol formation for itself. As a result, conjugated enones are usually obtained directly from aldol reactions without isolating the intermediate beta hydroxycarbonyl. Okay, yeah. Conjugated enones are more stable than non-conjugated enones for the same reason that conjugated dienes are more stable than non-conjugated dienes. Interaction between the pi electrons of the CC bond, C bond, and the pi electrons of the COO bond leads to a molecular orbital description for a conjugated enone with an interaction of the pi bonds over all four atomic centers. Yeah, alright, whatever. The real value of aldol dehydration is that removal of water from the reaction mixture can be used to drive the aldol equilibrium toward the product. Even though the initial aldol step itself may be unfavorable, as it usually is for ketones, the subsequent dehydration step nevertheless allows many aldol condensations to be carried out in good yield. Whoa. Cyclohexyl cyclohexanone? What the fuck is that? Dude, I gotta look that up. Cyclohexanone. That's a weird molecule. cereal diseases. Oh shit, okay, yeah, it's literally cereal. It's a pretty cool molecule. Wait, this is not it. Okay, wait, didn't I already do this one? Oh no, you know what? Wait, I want to read the phrasing. The aldol reaction product and the aldol condensation product. They're two different things. All right, I'm down. Let's do it. Okay, we have the enolate, and then we have our starting. Swing it down and around town. Okay, so now we have. And now we're just going to add base. So I'm going to take that, take that, take that. Okay, now we have our enolate, and what we're going to do is we're going to swing these down, down, down. Ooh, that's a nice way to draw that. With the pentagons facing each other. Low-key carbonyls are the most important of everything. All right, I'm just gonna crank them out. Okay, so H, there's no alpha protons on the phenyl side, so the base comes, pops that B off. Okay, now we have phenyl, O minus. We have our enolate. Then we have the starting. And this is going to do the standard thing. And we're going to map our carbons and not fuck this up. Okay, this is that carbon, so this is our O minus. We have the methyl, and then we have the final phenyl. Nice. Okay, I got this right. So now we just do the standard thing, you know, pop it, pop it, pop it, pop it, pop it, pop it. Okay. That's the thing about repetition is it gets so fast that things just get so easy. Bang. Bang bang. That one's easy. Is this a curveball or no? Okay, so these are the alpha protons. So then we're gonna get our enolate here. And then this swings down, this comes. Maybe I'll just do it. I gotta get to the Michael stuff, but alright, so we have 1, 2, 3, 4. 1, 2, 3. This is just 3-methyl butanol. Okay. Wait, this can't be right. Is this right? This doesn't seem right. Oh yeah, this is wrong. One, two, three, four, 5, 6, 7, 8. Okay. What is that little unit? Oh no, no. You know what I'm looking for? I'm looking for isoprene. Isoprene. Oh, interesting. Yeah, but it is isoprene is a see now that I know a little bit of like alkene chemistry, like there's a familiarity there. That's like, oh, well, there's like a reason for the stability and like why we're even talking about this stuff. Okay, so I think that's the whole molecule, right? Let me look at the answer. Um, that looks kind of weird. I don't know. Oh wait, is that the right? Did I do it wrong? CH. Wait, what? Please have a better drawing in here. I really hate those drawings. Oh, wait. Oh, you know what? It's because I forgot the methyls. That's it. That's okay. Dude, that's not even close to what it is. Wait, is it? Maybe it is. This might be right. Wait, 7? Oh, shoot. Okay, I think it's right. I think it's right. All right. Using aldol reactions in synthesis. Um, the aldol reaction yields either a beta hydroxyaldehyde ketone or an alpha beta unsaturated aldehyde ketone, depending on the experimental conditions. By learning how to work backward, it's possible to predict when the aldol reaction might be useful in synthesis. Whenever the target molecule contains either a beta hydroxyaldehyde Whenever the target molecule contains either a beta hydroxyaldehyde ketone or a conjugated enone, it might come from an aldol. Yeah. Okay, so we can extend this kind of reasoning even further by imagining that subsequent transformations might be carried out on the aldol products. For example, a saturated ketone 2-ethyl 1-hexanol. I always forget the reduction oxidation rule, or like what does what. NABH4. Yeah, I didn't know that H2 with a metal catalyst could do it. That's pretty good. That's pretty sweet, actually. That's like a really cool reaction. All right. I would do the problems, but it's getting very late. Only so much chem you can do. Well, that's cool. That's actually dope. I should use that. I should use that more. Oh, here we got the cross. Okay. Mixed aldol reactions. Until now, we've considered only symmetrical aldol reactions in which two carbonyl components have been the same. What would happen though if an aldol reaction were carried out between two different carbonyl partners? In general, a mixed aldol reaction between two similar aldehyde or ketone parts leads to a mixture of four products, or more generally, N squared. For example, base treatment of a mixture of acetaldehyde and propanol gives a complex mixture containing two symmetrical aldol products and two mixed aldol. Oh yeah. Clearly, such a reaction is of no practical value. On the other hand, mixed aldol reactions can lead cleanly to a single product if either of the two conditions is met. All right, intramolecular aldol. All right, I gotta work this out because this is sick. All right, so we have dimethyl ketone, and so what's gonna happen here is one thing that I want to know is there a preference for which the because if we take off these protons, my feeling is that you would prefer to take off these protons because uh all right, so I'm just gonna work through that. Okay. Yeah, that one's pretty straightforward. Wait, here, there's probably some interesting stuff in here. What the hell? Yeah, now I have to see that. So what happens here? So we have this is the alpha proton. So boom, boom. Hmm. Hmm. Yeah. That's pretty wild. Oh, see, actually, in this case, they don't show this whole intermediate analyte thing. The selectivity observed in the intramolecular aldol reaction of 2,5-hexane dione is due to the fact that all steps in the mechanism are reversible, so an equilibrium is reached. Thus, the relatively strain-free cyclopentenone product is considerably more stable than the highly strained cyclopropene alternative. For similar reasons, intramolecular aldol reactions of 1,5-diketones lead only to cyclohexenone products rather than the more strained acyl cyclobutenes. Okay. I don't know where this cyclobutene thing came from. Oh, wait. This is a 2,5-hexane dione. This is a 1,5-hexane dione. So yeah, if you did this, you'd form a cyclobutene, but not really. All right. All right. Claisen reaction. Esters, like aldehydes and ketones, are weakly acidic. But they're like really weakly acidic. Like their pKa on those hydrogens is like 25, I think. Yeah, it's 25. So weakly acidic is right. Okay, so we learned that the alpha protons of an ester have a pKa of about 25. And my book is saying that ethoxide, which is the conjugate base of ethanol, will somewhat take off one of those protons. And I'm wondering why, because presumably the stronger acid wins, and the stronger acid is ethanol. So ethanol will give up its proton to the alpha carbon, meaning that the alpha carbon will not be deprotonated. So what is the difference between a Claisen condensation and an aldol condensation? What is the difference between a Claisen condensation? Oh wait. Oh man. Oh, I think it's time to stop. I've lost steam. I feel like I covered a lot of ground now. I just have to do um like 5 more sections and then probably a bunch of problems. And then I also want to do my teacher's problems, which are way better. Like there's this one. Whatever. I'll end it now. 5 hours. That was a good 5 hour study session, actually. I think so.